Now I'm delighted to be able to introduce Patrick de Buhan, who graduated from École Polytechnique and École Nationale des Ponts et Chaussées in Paris before obtaining his doctorat des sciences from the University of Pierre et Marie Curie in 1986. Presently, he's professor of structural mechanics, so plasticity and yield design at École de Pont Paris Tech, and has been head of a research group for many years working in the field of micromechanics and structural analysis applied to civil engineering problems. He's very interested in the application of homogenization methods and related upscaling techniques, the simulation and design of reinforced geotechnical structures, and the development of associated engineering-oriented computational methods. We're going to hear about that today as he talks about the application of yield design theory to stability analysis of reinforced soil structures. Patrick de Buhan, the floor is yours.
Thank you very much for your kind presentation. We go back to yield design here, and you see on the title, the fundamentals of which have been presented yesterday morning by Jean Salençon, and we are trying to apply this concept to reinforced soil structures. The objective is to devise a computational method and a related software oriented design computational method. And for that, we need to use different models of reinforced soil I will present to you. Okay. First of all, a few pictures about what we are speaking about. We are speaking about reinforced soils, such as the well-known reinforced earth walls here, which was invented almost 60 years ago by Henri Vidal in France. The second type of reinforced soil we are concerned with, soil-laid excavations, where the excavation is reinforced by the introduction of metal bars called nails into the soil in order to stabilize the excavation. A third example of reinforced soil is rock bottle tunnels, rock or soft rocks or even soil, and reinforced by metal bars, which are the same as the nail or about the same, and in order to stabilize the underground excavation and prevent it to collapse and to converge too much. And finally, a fourth example is the reinforcement of soil foundations, foundation soils, and piled raft foundations. Well, the characteristics of all these reinforcement techniques is that, and the point of view I will adopt here, is that the reinforced soil may be regarded as geocomposite materials, as for industrial composites, at a different scale, of course, and in which the reinforcing inclusions are made of a constituent material, for instance, steel, polymeric material, or concrete, which exhibit a much higher resistance than the surrounding matrix, that is soil or rock. Okay. Okay, and we are interested in stability analysis of the reinforced soil structure by means of the yield design approach. For that, I want to recall the basic concept of the yield design reasoning. It consists of checking the compatibility in the mathematical or logical sense between two important concepts: the equilibrium, the static equilibrium of the structure on the one hand, and on the other hand, the strengths failure conditions, which should be verified at any point of the structure. And this compatibility must be verified, must be checked under prescribed or given loading. That's the basic concept. As you can see, the two conditions, the two keywords, equilibrium and strength or failure, these conditions are expressed on internal stresses, internal efforts. And so we are, for reinforced soil, we have a need to model in an appropriate way such reinforced, such internal forces. And for that, okay. Okay. There are three possible mechanic models of reinforced soil, which will be presented hereafter. The first one is called the mixed modeling approach. That is, the soil is modeled as a three-dimensional continuum, a Cauchy continuum, stresses, and while the inclusions are modeled as one-dimensional structural members. The second possible mechanical model, and we will see afterwards in which conditions it can be used, it's a homogenization method, according to which the reinforced soil as a whole can be regarded as a homogeneous but anisotropic continuum due to the preferential orientation of the reinforcement. And finally, the multi-phase model we will introduce is conceived as an extension of the homogenization method. Get to the slide. So first, okay. The first is a mixed modeling approach of reinforced soils in the context of digital design. This concept of mixed modeling is already conveyed in classical stability analysis by failure surfaces. Indeed, if we consider, for instance, a limit equilibrium approach, classical limit equilibrium approach, and we consider the equilibrium of the soil, this block of soil bounded by the failure surface here, and you must ensure the stability of this block, and with the resisting contribution on the one hand of the soil, following the distribution of normal and shear stresses developed along the failure surface, and of course on the reinforcement, and which are generally modeled as with the normal shear force and bending moments, that is generalized stresses. And we will keep this description and generalize this description to consider the mixed modeling approach of reinforced soils, in which you have two stress distribution, a first stress distribution in the soil through a stress field in a soil mass, and of course a distribution of a normal shear force and bending moment along the different exclusions, which are modeled as structural elements. You have also for two-dimensional elements, for instance, for geotextile, geogrids, and so on. Implementation of the yield design reasoning, and I will focus on a very simple illustrative example. The example is the following. You have a reinforced vertical cut of height h, reinforced by one row of inclusions and subjected to the soil loading parameter, which is a specific weight of the soil. The strength condition of the soil is, of course, the more Coulomb strength condition with the cohesion C and the angle of friction phi, which is called condition number 1, while the condition on the reinforcement are given through what we call an interaction formula, which is very classical for structural engineers, where appears here quantities which are N0, V0, M0, which are the normal and shear strengths of the inclusion, along with the bending strength or flexural strength of the inclusions M0. The case of flexible inclusion is a case when V and M equal 0, that is the inclusions are able to resist only to axial compressive force only. So the statement of the yield design problem on this kind of structure, you see it's easy to see that the stability of the excavation is governed by the non-dimensional parameters gamma h over c, which must be less than gamma plus, which is a critical stability factor. And the definition in the sense of the yield design theory of this critical stability factor is the following. Gamma is less than or equal to gamma plus if and only if one can exhibit a stress field in the soil along with generalized stress distribution along the reinforcements. They must be in equilibrium with the loading, gamma here, and satisfy the strength condition, condition 1 for sigma and condition 2, interaction formula for NV and M. The critical stability factor, gamma plus, from simple dimensional analysis argument, it is maybe shown that it is a function of the friction angle phi, and non-dimensional parameters R, V, and M, which relates to the strengths and the normal shear strength of the reinforcement along with the bending or flexural strength. Okay. It may be proved that the lower bound, remember, I should remind you, two approaches, the lower bound static approach and the upper bound kinematic approach. In such a case, in the case of mixed modeling, the lower bound static approach proves to be difficult, if not impossible in certain cases, to implement. So we made a choice here to implement the kinematic approach of yield design. I have some problem with that. Okay. A simple analytical upper bound kinematic approach will be used on the problem under consideration. We consider here a virtual translational failure mechanism where triangular wedge OAB is moving downwards, bounded by a plane, a failure plane AB, inclined angle alpha with a vertical, is given a rigid body motion through a velocity, a virtual velocity u. And according to the upper bound kinematic approach, we have to compute two quantities. The first quantity is what we call the virtual work of external forces. The result is given here, and you can see that it involves the weight of the block OAB. And on the other hand, you have to calculate the maximum resisting work along the failure plane here, which contains two quantities, two additive quantities. The first one is relating to the soil, which is proportional to the equation here, with the angle psi, the angle of inclination of the discontinuity with the failure plane must remain comprised between phi and pi minus phi. And the second contribution to the resisting force is generated by the discontinuity in the reinforcement, which is induced by the discontinuity in the soil. And the expression here, and it involves, of course, the strength characteristics of the reinforcement, namely the axial strength and the shear strength. So the kinematic theorem of yield design states that for the stability of the excavation, a necessary condition, a necessary but not sufficient condition for the excavation to remain stable is that whatever the failure mechanism, the work of external forces remains less than the maximum resisting work. And this leads to a first upper bound here, gamma plus less than gamma UB, which is a function of alpha, the inclination of the failure plane, and psi, the inclination of the velocity discontinuity with respect to failure plane. These are optimization parameters. It is easy to see that the minimum upper bound is obtained. Okay. The minimum is obtained for psi equals phi, and the angle alpha here, which is given by the relationship here. And the expression of the upper bound solution, the upper bound estimate of the critical stability factor is given here. And of course, it involves the classical passive earth pressure coefficient here. Two particular cases. The first case is a case of unreinforced excavation, where N0 and V0 are equal to 0, and gamma plus, the upper bound, is simply the classical result, 4 times the square root of Kp. Now, the reinforcement with flexible inclusions, that is V0 equals 0, but not N0, and you have this expression here, where N0 appears here. So, of course, you can see that the case, this upper bound is greater than this one, and this upper bound is greater than that one. The question, important question to be asked is, to what extent should the shear and bending strength of the response be taken into account? Okay. For that purpose, we have undertaken almost 30 years ago a parametric study on the stability of a uniformly reinforced excavation. You have a uniform excavation, with a friction angle equal to 0, that is a soft clay, for instance, with a specific weight gamma. And we implement the upper bound kinematic approach using failure mechanisms, rotational failure mechanism, bounded by slip circle. It's a slip circle analysis, classical use. In doing that, we have the following results, and we optimize the upper bound with respect to the coordinates of the center of rotation. The results have been obtained in 1993. And here represented, we introduce the coefficient of reinforcement, the definition of which is shown here. And what we are going to see is the variation of the upper bound of the critical stability factor divided by 1 plus R as a function of the coefficient of reinforcement. And we obtain 2 curves. The first curve is a case where the inclusions are flexible, that is V0 and V0 none, and we have this curve, red curve here. And the case where the shear bending resistant inclusions, and typically we have selected the following values here correspond to a soil nailing technique. And here you see that you have, of course, an upper bound which is much greater than the upper bound calculated in the considering the flexible assumption. To give an example, for R equals 4, you have a 27% increase of the lower bound. That is, but now the idea is used to improve such lower bounds, that is lower bounds, and we are doing that. We're using a rotational mechanism with shear zone. These are based on experiment observations. Here you have a view of an experiment, a full-scale experiment of a soil nail structure, which was brought to failure almost more than 30 years ago in the frame of the French national project Clés. And you may see the failure here. You have a kind of shear zone, a gray shear zone of the soil. And more importantly, you can see the deformation of the nails, which are in deformation, without bending deformation, and not shear, a sharp discontinuity in the shape. This suggests to use generalized failure mechanism in which the slip circle is replaced by a ring-shaped or annular shear zone, the thickness of which is taken as minimization parameters. So we have 3 minimization parameters, the coordinates of the center of rotation along with the thickness of the shell layer. In doing that, we obtain the following results. That is the green curve. You see that it is still above the curve number 1, but well below the curve number 2. That is the difference, the improvement of the stability is only 5%, and not 25% as predicted by the slip circle analysis. So the conclusions for this first part: the contribution of the shear bending strength is always positive, of course, but in many cases it is not as important as could be expected from a slip circle analysis, at least for nails. And the second conclusion is that it should be, it is always possible to employ mechanisms with velocity discontinuity surfaces, such as a slip circle analysis, but by adopting a reduced shear strength of the inclusions, that is mu V0 instead of Z0, where mu is a reduction factor. For instance, for nails, it could be related to 0.1. So now we move to the second model. Yield strength, a homogenization method where the reinforced soil may be considered as anisotropic media. This model is applicable to reinforced soils which are densely and regularly reinforced by identical inclusions. Here you have a view of pile foundations, which has been reinforced by a network of piles, of inclusions, and subjected to vertical loading. You see upon two conditions, you can replace the reinforced zone, which is heterogeneous composite, by a equivalent homogeneous medium, provided two conditions are verified. The first condition is, of course, the periodicity. And the second condition is that the epsilon, which is we call the scale factor, that is the ratio between the spacing between two occlusions and a characteristic length of the whole structure, namely here the width of the foundation, be small, sufficiently small. From a theoretical point of view, there has been a yield design homogenization result which has been demonstrated. And referring to this bearing capacity problem, this means that the initial structure, the ultimate bearing capacity of the initial structure, Q plus of epsilon, tends to that of the homogenized structures, provided that epsilon tends to 0. But of course, this means that the method is based on the prior determination of a macroscopic strength condition. That's a condition for implementing such a homogenization method. This will be done in a particular but very important case of thin, highly resistant linear inclusions. Here you have a view of a reinforced earth technique. So with the soil of cohesion C and friction angle phi reinforced by a metal strip, steel strips. And if you have a cross-sectional view of this elementary volume, we have the universal strength of the steel, which is much larger. Here the sign is not the good, it's much larger. You have a double sign than the cohesion. But on the other hand, the volume fraction of the reinforcement, that is the cross-sectional area SR of the strip, is much lower, very small with respect to the cross-sectional area of the volume. In such a case, you can derive a closed form expression for the strength macroscopic strength conditions, which is defined as follows, denoting by capital sigma the macroscopic stress. This stress is verifying this macroscopic strength condition if and only if it can be additively decomposed into two components. I'm sorry for the mathematical notations here. A first component which is referred to the soil, which must verifies the more Coulomb strength condition. And the second component, which is a uniaxial stress, that means a stress tensor with only one component along the direction of the reinforcement given by a unit vector here, which simply must be comprised between 0 and sigma 0, it equals to n0 divided by capital S. I must specify here that I have adopted the convention that tensile stresses are positive. It's a convention inverse of the soil mechanics. Here, 0 means that you want to prevent the buckling, of course, and here the tensile resistance of one reinforcement may be calculated as a product of the cross-sectional area by the yield strength of the steel or metal, constitutive material. The interpretation of sigma 0, it says the tensile strength of the reinforcement per unit transverse area to the reinforcement. It can also be calculated as a product of the volume fraction. Okay, it doesn't work. Oh, okay. The volume fraction of the reinforcement, eta, which is SR over capital S, and multiplied by the sigma 1. Three geometrical interpretation of this criterion, which may help you to really understand what it's about. The first is the strength domain in the space of stresses, two-dimensional stresses, where on plane strain conditions, there are three components of the macroscopic stresses, sigma x6, sigma yy, and sigma xy, the direction of the reinforcement being along the x direction. You have here drawn in this space, this three-dimensional space, the strength domain of the soil, called JS, which is a conical domain, circular conical domain in blue. And here you have the strength domain of the soil, which is constructed as a convex envelope of the soil initial strength domain, and that the translation of the cone along the sigma x6 axis by the distance sigma 0. Of course, obviously, you have a reinforcing effect, since in all cases, GS is strictly included in GR. Second representation is in the deviatoric plane. This is a cross-sectional view along a deviatoric plane, which is a perpendicular normal to the isotropic stress axis. And here you have the same construction, the trace, the section, the cross-sectional section of the soil strength domain is given here. It's a disk, a circular disk, and here you have the same kind of construction as that done is here. And the third representation, which is perhaps more, which may be more evocating for soil mechanicians, is that you can represent the stress domain, the strength domain, for instance, on a facet. On a facet, here you have the strength domain of the soil. Remember that tensile stresses are counted positive here, so generally it's the other way, angle phi, and you may construct the corresponding strength domain in the same plane by this construction. And you see that this domain is a function of alpha, of orientation of the plane. That means clearly that the macroscopic, you have a strength anisotropy, an obvious strength anisotropy. 3 minutes? It is 45, no? It's 30. It's 30. Oh, okay. I thought it was 35 on the program. No, 45 on the program.
It's fine, carry on.
I'm sorry. Okay, say well, we'll skip this transparency, this slide, to get to the. Okay. And we just give an application of this yield design homogenization. Here, which is shown here. Here we have stability of reinforced earth retaining structures. Here the results which have been computed almost also 30 years ago. And you have three curves here, which are the kinematic upper bound with log spiral mechanism, the finite element-based kinematic upper bound, that is the velocity fields are generated through a finite element discretization, and the finite element-based static lower bound. And you see that you have quite good performance of all the methods, since the relative gap between the upper and lower bound is between 2 and 5%. Only 5 minutes? I cannot, no, it's not possible. Okay. I move to the third model, which is a multi-phase model, which is conceived as an improved homogenization method. As you can see, the homogenized method fails to capture the shear and bending strengths of the reinforcement. The parameter sigma 0 is only the actual strength of the reinforcement. And the multi-phase model here makes it possible to account for such a strength condition. In such a model, the reinforced soil is model is a superposition of two geometrically distinct continuum phases. One, the soil phase, the second, the reinforcement phase, and you have, which are in mutual interaction through body force density. Well, I skipped all the. Okay, I skipped that too, and I go directly to the example. Okay, so I skip that too. Okay, application stability analysis of a piled embankment under earthquake loading. I will take 5 minutes for that. Here you have a piled embankment. The embankment is made of a purely frictional soil with a phi equal to angle phi at 35 degrees, and lying over a soft clay layer with a cohesion of 20 kilopascal. Both soils have the same specific weight here, and they are reinforced by a network of piles. And we are going to calculate the stability of this structure. The loading is the seismic loading, which is characterized by a non-dimensional parameter K, and the stability, and we are looking for the ultimate value of the stability factor K+. We derive upper and lower bound estimates with a finite element formulation here, just to discretize the velocity and the stress field. It's not a finite element method, classical finite element method. And this is associated with this convex optimization procedure. Some of them have been presented yesterday by Professor Kradmanhoft. The results are the following. Okay. In the case of unreinforced embankment, you have the failure mechanism shown here, and you have the values of the upper bound and lower bound are very close to each other, and it is close to 0.04. The case of flexible inclusions here, this point here, where it goes from 0.404 to 0.107, and the case of bending resistant inclusions, that is the point here with the arrow here, which becomes equal to 0.16. Okay, I will stop here if you don't mind. I had some conclusions, but I think it's perfect. Okay. They are long, the conclusions. Okay. Concluding remarks. The implementation of the design approach and reinforced soil structure when trying to deal with the problem, we come across two situations. The first situation, only a very small number of inclusions are placed in the soil following no regular arrangement. In that case, the mixed modeling approach appears to be the most suitable way of dealing with the stability analysis of such structure, predominantly in the context of the upper bound kinematic approach. The mechanism with failure surfaces can still be used, taking the resisting contribution of the reinforcement into account in an appropriate manner. And the most frequently encountered situation when a large number of regularly distributed inclusions are involved, the implementation of a multi-phase model perceived as an improved homogenization method allows to obtain accurate bounds on the ultimate bearing capacity of this type of reinforced structure. And there is a last one. It's outside. The model may easily incorporate shear and bending strength characteristics of reinforcement, contrary to the homogenization method. As well, I didn't say anything about that, as well as a failure condition at the soil inclusion interface. We didn't consider here. So I stop here. I'm sorry.
I'm sorry for hurrying you up. I was
no.
30 minutes.
I thought it was 45 minutes.
There was a disconnect, perhaps, in there. But I'm sure there'll be lots of questions, because that was absolutely fascinating with the mixed model, the multiphase, and the homogenization. Would anybody like to start? So I'm going to give you one then on the homogenization, because I think it's really an interesting way of dealing with a problem. But when you have to worry about the vertical settlements, for example, of an embankment on homogenized ground, and you have to worry about the lateral movements at the edges, then you have anisotropy in such a system. And then when you have to deal with the strength aspects as well, so to try and get factors for the whole thing, that is, it's easier when you know what the end result is to feed back. How do you find it really works when you're comparing the three systems for a similar problem to use homogenization? Yeah.
You mean there's three models?
Yes.
Okay. As I said here, it's a mixed modeling approach is suitable in any case. You can use this approach, but you can use only the upper bound kinematic approach with failure surfaces. You cannot go further. It's very, very hard to go further, and you cannot use the lower bound static approach. But the multiphase model, or the homogenization, is only applicable to the case of densely reinforced soils, as shown here. And the advantage of this model is that when you, for instance, you use a numerical finite element discretization of a structure, as shown on one of my slides, you've seen that the reinforced node, the mesh is not much finer than the outside. No. You treat this zone as if it was homogeneous. You have not to capture the strong heterogeneity between. So you get a quite simplification and sharply reduced computational times.
Sounds great. Thank you very much.
No, that's...
Thank you, Jean-David Verne, Unilassal. On the example you gave, page 31, you said that the lower bound static approach...
31.
Yeah, page 31. We'll have a long way to this.
It doesn't work very well.
Well, no,
okay.
It's just to ask you, is there a theoretical principle that explains why this lower bound static approach is hard or even impossible in such a case?
In the mixed modeling approach, you mean?
It was on one of your examples.
In the mixed modeling approach, you have to implement the lower bound static approach. You have to construct and to exhibit stress fields. I mean stress field in the soil, sigma, and stress distribution, generalized stress distribution along the reinforcement. For instance, in the case of three-dimensional, so you have a three-dimensional continuum inside a one-dimensional bar, you cannot express the equilibrium of that. You have a problem with in 3 dimensions, and you cannot cannot construct statically admissible stress field.
But is this a mathematical problem, or rather the problem that it's statically undeterminate?
No, it's not.
Underdetermined, I mean.
No, it's not undetermined. That is, you have a contradiction between the equilibrium equation of the reinforcement of the beam as one-dimensional, and the equilibrium equation of the soil, which is a 3-dimensional continuum. We cannot connect each other. Only in the case of plane strain.
Okay.
In plane strain, you can do it, but in 3-dimensional configuration, you cannot do it.
So then, in such a case, you won't have the two possibilities you have, which is the upper bound and the lower bound. So isn't this a problem, generally speaking? Because normally you want the two of the solutions.
It's not really a problem, since in geotechnics it's mainly the upper bound kinematic approach which is used.
Okay, thank you.
The lower bounds are there for reassuring the quality of the upper bound. If you have a lower bound which is very close to the upper bound, you have a good quality of the upper bound. That means that's all.
Well, Patrick, do we have any experimental results to compare with those theoretical? Maybe.
I have none.
Okay, we have...
Yes.
Yeah.
Yes.
For the Rion Bridge, we use the mixed modeling approach with the kinematic...
It was mixed modeling.
It was mixed modeling and with the shear zone, as you presented.
Yes.
And we have validation with centrifuge test.
Oh, yeah, okay.
And we were very close to the results.
Wait, I thought about the homogenization.
No, you did not develop that at that time. So.
Okay, well, of course.
We'd also published some data actually on embankments constructed, 3-dimensional embankments constructed on very, very soft, normally consolidated clay in a drum centrifuge at different spacings of stone columns. So, but I think, again, getting the parameters for that and comparing it in a valid way might not be so easy. But again, you could get graphs looking a little bit like this.
It was columns, stone columns?
They were sand compaction piles.
Oh, okay, stone columns.
Put them stone columns effectively.
These models are not applicable to such reinforcements.
No.
Because the characteristics of the stone, of the reinforcement strength is not much higher than the surrounding stone.
And also you get different things going on around the boundaries as a result of the...
You may apply the homogenizing method, but it's much more complicated than...
It is. Not so easy. Other questions? There we go. Somebody at the back. Oh, brilliant. No, don't say sorry. Running up to the back. Say on.
Thanks a lot for the presentation. So Nathanael Saval from Polytech Clermont. I have maybe one dumb remark on your result when you present the FEM upper bound and the log spiral. It appears that the log spiral is much better in terms that, and it's very funny. I'm not much better. I mean that the FEM does not catch the, let's say, the best velocity field. I think it was in slide 40.
Yeah, that's a good question.
Is it generalized to geotechnical problems, or is it just a particular case where here the log spiral is working well?
Okay, thank you. It's a very good question. I try to come back to the...
It's 40, so we're close to the end.
If I had a computer, I could have done it. Okay, your remark is an excellent remark. You observed that it was, I think, a dotted red line, which. You have time. Going back, I think. Okay, I think it's not.
Maybe it was 39.
Okay, this one. Okay, you're quite right. The dotted line here corresponds to the log spiral, use of log spiral mechanic, and this underlines simply the excellent performance of such mechanism, even with respect even with respect to finite element based. At the time, it was in 30 years ago, the finite element solutions in yield design and limitations were not very performing. So maybe now we could lower this bounds. But you excellent remark. Since the relative gap between the bounds is between 2 and 5.
It's nothing. I agree.
But you're quite right.
And maybe a second remark regarding when you present the velocity field of yield design. When you presented the latency angle, I think it's too early in the presentation, so maybe we can keep just talking. Why do we have the psi which is compulsory bigger than phi? Why couldn't we in yield design say okay? Because I understand in FEM we should have this associative rule, but why do we have in yield design also this coercitive constraint?
No, the condition on involving psi, which may be comprised between phi, the friction angle, and pi minus phi, is simply the condition for being able to compute the maximum resisting work. If it is outside, it goes to infinity, so there's no interest. And you have in the yield design approach, you have no consideration of the associative plasticity and so on. There's nothing to do.
That's why I was asking, but you answered the question because you said if it goes below phi, then it goes to infinity, and so you cannot compute anything.
That's right.
Thanks a lot.
Okay.
Thank you very much. We have 2 minutes. Does anybody want a very last question? I'd like to see one of the other younger people ask a question. Is there somebody got a burning question, please? Burning question. Burning question. Not burning. The coffee's burning, I think, otherwise it's the other challenge of all of this. I just want you to generate the younger generation, Patrick. I'm really sort of grey-haired and all the rest of it.
I know I'm from the old generation.
No, we want to just, it's a good start, no? Oh, well, I think everybody feels... Oh, there we go. There we go. Thank you very much.
Jean-Baptiste Peyer, Switzerland. I will try it in English. You said, considering thickness for the shear failure, there is only 5% of difference between the nails and the one-dimensional reinforcement. Is that true, or is that a limitation of the model?
You're referring to the last slide of the...
Yeah, I don't remember. But yeah, I mean, is that this difference, or the influence of the resistance by bending, is that so slow? There is only 5 difference between a nail and a...
there is a difference of 5%, a gap of 5% between the calculation when assuming that the reinforcements are flexible, and the case where shear and bending moments, bending strengths are taken into account. That's right.
Yeah.
For nails, if you replace nails by large diameter piles, for instance, the result will be completely different. As shown in the last transparency, you see that the diameter of the piles is very important.
But for a nail with one given diameter,
yes,
if you consider the shear resistance and bending resistance, and only the tensile resistance, there is only 5% of difference.
Yes.
Okay. Interesting.
On this problem.
Okay, but is that
is the gain in stability, which could be expected from taking into account shear and bending resistance, is relatively negligible.
Okay. Thank you.
I think on that note, the absence of coffee might have an impact more than the 5%. So I think we should say thank you very much to Patrick for having survived being bullied by me. So,